Hello friends, my name is Sudhir Bin and I welcome you all on my channel STAAD.Pro. Friends, in my last video I told you how to make geometry in STAAD.Pro and how to apply dead and live load in your STAAD model. Now in my today's video I will tell you how one can apply wind load in STAAD model. Okay guys, I have seen various videos in which video makers apply wrong wind loads. They use wrong methods to calculate wind load. Guys, what mistakes they do, I will tell you in my today's video. So let's start. So I am opening my last model. So this is my last model in which I told you how to apply dead and live load. So first of all, let me tell you how to calculate wind load as per IS 456. Okay, so let's assume that our building is in Mumbai. So the basic wind speed for Mumbai is given in IS code. So let's move to IS code 875 part 3 2015. This is the new version of IS 875 part 3. So in this we can see the basic wind speed at 10-meter height for some important cities is given. For Mumbai it is 44 meter per second. So let's take 44 meter per second. This is the Excel sheet which I have prepared to calculate wind speed, guys. If you want this Excel sheet, you can comment in comment section. So I will give you this Excel sheet also. So second term is terrain category. So let me show you what it is actually. Now as per IS 875 part 3, for wind pressure calculation, wind load calculation, we have to first calculate VZ, that is design wind speed, and for that we require basic wind speed, then then K1 as a probability factor or risk coefficient, K2 that is terrain roughness and height factor, and K3 topography factor, and K4 importance factor for cyclonic region. Okay, so as I told you, basic wind speed we are taking as 44 meter per second. Then K1 is probability factor or risk coefficient. So let me show you what it is actually. Risk coefficient, here is a table given for K1. So based on your structure's life and wind speed, you can take a risk coefficient, that is K1. Now let us assume that our building lifespan is 50 years. So and wind speed, since our wind speed is 44 meter per second, so I will take K1 as 1. So let's insert K1 as 1. Now this is K2, guys, and why I have taken this K2 here I will tell you. First let's move to K3, that is topography factor. This is the table for K2 which I have taken here, and K3 is given here. Okay, so K3 value is the effect of topography shall be significant at a site when upwind slope is more than about 3 degree, and below that the value of K3 may be taken to equal to 1. The value of K3 is confined in the range of 1 to 1.36 for slopes more than 3 degree. So we will take K3 as a 1. Then there is a one extra term introduced in IS 875 part 3 2015, that is importance factor for cyclonic region. If your structure is in a region where cyclone comes, so in that case you have to take this factor as 1.3 or 1.15 for different structures as mentioned here, and all other structures we have to take K4 as 1. So let us assume that since in Mumbai cyclone rarely comes, so we will take it as 1. So I am taking K4 as 1. Now wind directionality factor. So based on these values K1, K2, K3 and K4, first I will calculate VZ, that is design wind speed. Okay, so here I have calculated design wind speed as D6, that is D6 basic wind speed into D8, that is K1, into D17, that is K2, then D9 is nothing but K3, and D10 nothing but K4. So I have multiplied here basic wind speed into K1, K2, K3, K4. So this is nothing but my VZ, that is design wind speed. Now why I have multiplied 0.6 and square here? For that we have to go to next page, that is design wind pressure. Here you can see wind pressure at certain height is equals to 0.6 into Vz square. Vz, that is this, nothing but this. This is a Vz. So Pz is equals to 0.6 times Vz square. So here I have calculated that only Pz is equals to 0.6 into Vz square. So now let's talk about K2. As we know that wind speed will differ at height by height. So for different heights K2 factor is given. So basically our structure's height is around 12.6 meter. So in code values are given, so we will take 10, our building falls in this two range only, 10 to 15 meter height, because our building height is 12.6. So for 10 meter height, let's consider our terrain category as 3. So our K2 factor for 10 meter height will be 0.9. So for 10 meter height, 0.91, put 91. Now for 12.6 meter height, since here after 10 meter height directly 15 meter height value given, so we have to interpolate to get K2 factor for height of 12.6 meter. Here it is mentioned that interpolation is permitted, so if you can do interpolation to get your intermediate value. So after interpolation I got it as Let me calculate it. So for 10 meter, then 15-meter height it is given. For 10-meter height it is given as 0.91, and for 15.97. So, and I need it for 12.6. So it is 0.9412. So 0.9412. So as height is increasing, K2 value is also increasing, guys. So definitely our pressure will also increase, as K2 is directly proportional to PZ. Okay, because in PZ calculation K2 is coming, and that is directly proportional to it. So when K2 will increase, PZ will also increase. So we have calculated PZ value for height of 10 meter and 12.6 meter. Okay, so we have completed till here. Now let's move towards design wind pressure. So design wind pressure is nothing but is equals to Kd into Ka into Kc into Pz. Now here Kd is nothing but directionality factor, wind directionality factor, and K is area averaging factor, and Kc is combination factor, and Pz is nothing but this. So what is Kd? Let's see. Kd is wind directionality factor, and it can be taken as zero point 0.9 for lattice framework, truss towers, etc., and for circular or near circular, for this factor may be taken as 1. So, and for buildings also it can be taken as 0.9, so we will take it as 0.9 only. Kd 0.9. Then area averaging factor. Area averaging factor is given here in table 4. So as per the definition, a tributary area is nothing but the center to center distance between frames. So in our case, center to center distance between column is 4. Let's see, it is 4. Okay, so we are taking it as 4 into 9.6 height. So this is nothing but our tributary area, 4 into 9.6. So let's see what it comes. 4 into 9.6, it is 38.4 meters square. So this is greater than 25. So linear interpolation for intermediate value is permitted here also. So you can calculate it. For instance, I am taking it as 0.9 only. So area averaging factor, I am taking it as 0.9. You can calculate actual value by interpolating. Now for combination factor Kc, we have to go to 7.3.3.13 clause. So let's go 3. It's given quite below. Yeah, here you can see, when taking the combined effect of wind load on the frame, a reduction factor of 0.9 may be used over building envelope when roof is subjected to pressure and internal pressure is suction, or vice versa. So it means that, guys, if you are considering internal as well as external pressure, that that time you have to take it as zero point 0.9, or if your structure is open structure, that means there will be no internal pressure or internal suction. In that case you can take it as 1, but since in our structure we will take internal pressure coefficient also, so we will take it as a 0.9. So here guys, this P is nothing but design wind pressure. So this is PD, design wind pressure, which is equals to KD into KA into KC into PZ. So design wind pressure is equals to KD into KA into KC into PZ. I calculated it for 10 meter height also and for 12.6 meter height also. Now there is a clause mentioned here that the value of PD however shall not be less than 0.7 times PZ. So we have to compare 0.7 PZ and PD, and whichever is greater we have to take it as design wind pressure. So let's calculate first 0.7 into PZ. So this is 0.7 into PZ. This is PZ into 0.7. So value is coming out to be 0.673. So we have to take maximum of these two. Since 0.7 is max more than 0.67, so we are taking as 0.701 as our design wind pressure. Similarly for 12.6 meter height also. So guys, we have calculated design wind pressure. Now only part is remaining is to apply it in STAAD.Pro. So let's do it. To apply it in STAAD.Pro you have to go to load page and this definition part. In this definition part you have to first define wind definition. Click on it and simply add and name it as wind. Click add. Now let's add in STAAD.Pro guys. In IS 875 provision is not given for wind load calculation. Only you can calculate it by ASC code and Russian code only. And for other codes you have to calculate with pressure and you have to apply it here. So that is why I had calculated this wind pressure manually. So now let's put these values here. 0.0701 kilonewton per meter square for up to 10 meter height. And next is 0.750 for 12.6, 0.750 for 12.6 meter height. Okay, and add. Now this page will open up. This is nothing but a solidity ratio factor. I've seen many that they use it but they don't know what it is actually. So this is nothing but solidity ratio. And what is solidity ratio? Let me tell you. Here a definition of solidity ratio is given. The solidity ratio is equal to the area of obstruction under the canopy divided by the gross area under the canopy. Means if this is my gross area of a building of this face, and suppose there are certain windows, so if I deduct those opening from my total area, I will get area which is actually obstructing the wind. So and if I will take the ratio of that, I will get a factor which I will apply here. So let's assume that it will be 0.95. it is indicating that this phase has certain openings. So I'm taking it as 0.95 instead of taking 1. Click add and click assign to view. Yes. Okay. Now we have defined wind definition. Now let's go to load case and add a wind. Here take loading type, select as wind and define here wind X. So add it. Now let's add wind. Here you can see a wind load page. So now this is select X direction, and this is the factor which I have seen everyone applying it incorrectly. This factor they keep as it is, but actually this is a force coefficient factor and you have to calculate this value. You don't have to simply put it as 1. You have to calculate it, and how to calculate it I will show you guys. This is external pressure coefficient for walls of rectangular clad building. Since my building will have walls, so for that I have to calculate coefficients. So first let's see our building fall in which category. For that we have to take height to width ratio. So here I have calculated it is height. My building height is 12.6 and 8 as a width of building. Here I have taken minimum width as 8. So I am getting it as 1.575. So our building falls in 1.575 in this category, that is greater than 1.5 but less than 6. Now let's move to second criteria, that length to width ratio. Now length of my building is 11 and width is 8 meter. So this is coming out to be 1.375, that is greater than 1 and less than 1.5. So we have calculated that our building comes in which category. So it is falling under this category. So now since we are calculating wind X, okay, you can see here that this is the direction of wind. So when my wind is blowing in this direction, my coefficient are higher side. For A phase, coefficient is this one. We have to take this one. Coefficient is on higher side, 0.8, and for leeward side, that is B, it is lower side as 0.25, and for remaining phase C and D also it is 0.8. Okay, now similarly when my wind will blow from 90 degree, that is from this phase, or in our case from Z direction, it will be, for Z it will be 0.8, and for D phase it will be 0.25, and for remaining it will be 0.8. Okay, so here I have calculated it 0.8. Here I have written it as, let's make a box. Okay, so here 0.8 I have taken from here, and 0.25, 0.8 also I have written here, 0.8, 0.8 and 0.25. Okay, so let's correct it, 0.25. Now what is this? This is nothing but internal pressure coefficient, and you can take it as 0.2, 0.5, 0.7, depending on your percentage of opening, depending on permeability of your building. So I am considering that my building is less permeable, that is opening percentage is very less, so I am taking it as 0.2. You have to calculate what is the percentage of opening, but for since time is less, so I am considering it as 0.2 only. So now since my wind is blowing from this direction, so most critical case for this phase will be that wind is going this way and internal pressure coefficient is also moving in this direction. So for here formula is given that CPE minus CPI, external pressure coefficient minus internal pressure coefficient, and we have to add this coefficient algebraically, that is with sign or with sign. So this is my external pressure coefficient and this is minus sign, and this is my internal pressure coefficient. Since I have taken it as minus 0.5 because most critical case will be this external pressure coefficient is moving towards the structure and internal pressure coefficient moving away from the structure. Away means away from this face. So that will be the most critical, and for away I have to take minus sign, so it is coming out to be 1.3. Similarly for this phase also coefficient is already minus 0.25 and minus sign from here, from this formula, and CPI I have taken as positive because the most critical case will be wind is blowing away from this side, minus 0.25 indicate that wind is blowing away from the face. So take it as positive, and so it is adding up. Okay, now for other faces also it will be same in same way. It is minus sign, minus 0.8, so is equals to minus, minus indicating that it is away from this face. The most critical case will be internal pressure coefficient is moving towards the face, so minus plus 0.2. Okay, I have not changed here, so let me change it as 0.2. Okay, so this part is remaining here also. Most critical case will be that this wind is moving in this way and internal pressure coefficient is also moving in this way, so the net will be maximum. So since it is minus as given in code only, minus 0.8, and in formula it is minus, so minus, put minus, then plus 0.2 because that will make a most critical case. So this is the pressure coefficients I am getting. In this case I got it 1 and 0.45. Now if suppose I would have taken it as 0.5, so this value will not come it as 1, it will be like 1.3, so I have to put this value here, and here I have to put this value CF. Okay, in our case it is coming out to be 1 only, so let's put it as 1 only. Simply add. This is for wind X. Now for leeward side I have to put 0.45, add. Then for Z direction I have to take 1 and again 1. Now let's see, let's correct it. Range, the maximum range of our building is 12.6, and wind load will not apply on the um, structure which is below ground, so we have to apply it from ground level, and our ground level is starting from 0, so minimum range is for 0 and maximum is 12.6 for Y. Change it, so you can see wind load is applying from here. Now for X range we have to take 0 and 11, and for Z is 0 and maximum Z is 8. It is similar as the floor area load only, which I had explained in my last video. Now for leeward face, so let's change it 12.6, maximum range is 11, and for maximum range for Z is 8. Change. Here guys, this open structure means if I have to design a pole or something which is a single structure, in that case I have to click on this open structure, so forces will apply on individual members like this. So we have to design entire building, so we will not click on open structures since our building have walls. So likewise you have to define wind. Now let's correct Z direction wind. So when wind is blowing from this side, rest of the part wind will go away from the faces. So for Z direction wind must go in this direction, so I have to put here minus sign, and let's correct ranges 12.6, and for ZZ it should be 0, so the wind is going away from the structure. Now for this Z direction, since I want my wind to blow away from this face, so I have to keep it as 1 only. So let's correct other range. This x maximum will be 11 and z range minimum is 8 and 8. Change. Okay, so this is the way guys you can calculate a wind load. Now let's verify whether we have applied it correctly or not. So you have to click your force in order to see wind load values. Here you have to right click, go to structure diagrams, click level, click load values. Okay, so you can see the load values here. Now let's verify our calculation that it is 2.131. So let's see. Now our center to center distance between column is 4 and floor to floor distance is 3.2. So half of the load is going to this column and going to this column, and half of the load is going to upper beam and half of the load is going to this lower node. So our area is half of the area we have to calculate, that is 4 by 2, that is 4 by 2, and here 3.2 by 2, that is height by 2. So my area, exposed area is 3.2, that is 2 into 1.6. So now let's calculate it. Wind pressure into area, exposed area, into coefficient CF. Here I have calculated it from this formula only. F is equals to CPI into A into PD. CPI minus CPI. CPE minus CPI is nothing but this, and A factor is nothing but this area, and this is PD into CPE minus CPI into area. Now since we had applied a solidity ratio as solidity factor as 0.95, so we have to again reduce it by 0.95, so I'm getting it as 2.13. so let's see our value is matching or not. So guys, here you can see our value is exactly matching with STAAD value 2.131. okay, so guys, this is the exact correct method which one should follow while defining a wind load in STAAD.Pro. So guys, practice it. This is the correct way. Similarly, you can define for other directions also. So if you have any doubt, please comment in comment section, and please guys, please like my video and subscribe my channel and share it. Thank you.